Hello, I'm Daniel. I'm a principal software engineer at Red Hat and a postdoctoral researcher at the Escola Superiore Sant'Anna. And in both cases, I work with real-time systems, but at Red Hat, I work from a more practical perspective, and at the university, I work with a more theoretical perspective. And today we'll talk a little bit about the joint of these two things in the real-time Linux context, right? Discussing the state of art of this and what is next, where should we go in the future, right? So it's worth saying that this talk doesn't aim to be like a very complex talk or deeply explaining all these context. Instead, it should be an easygoing, trying to create the context and explain the context of these things, but serving mainly as a starting point or an index of the things that are going on and the motivations that we have, right? So we'll start this talk with a brief introduction of real-time systems theory and what is real-time Linux, and then we'll discuss about the current users and the next users, right? And from that, from the conclusions that we have from the needs of the users that we have, we will discuss the recent findings of the applications of the theory and the practice in the analysis of the preemption on the preempt RT and the benefits of this analysis. And we'll discuss what is next, where else we can apply such a more sophisticated reasoning and testing and analysis of the Linux kernel, right? And we'll finish this talk with some remarks. But before starting, let's recall a little bit about what are real-time systems. So, real-time systems are computing systems where the correct behavior does not depend only on the functional behavior, but also in the timing behavior. In other words, the response time to a request is only correct if the logical result is correct and produced within a given deadline. And generally, the main metric here is about the response time of each task. The findings of the real-time systems theory are generally communicated through scientific papers. And these papers, they start with a clear definition of the system, capturing all the behaviors, and it's generally named the task model, right, of the system. Then, based on this task model, an algorithm is proposed, and later this algorithm is analyzed, trying to demonstrate that the worst case are known and somehow bounded. And this analysis is generally made in terms of mathematical reasoning, like with a theorem. And from this explanation and this analysis, a set of equations or models are proposed to conclude that the system can or cannot accomplish all the tasks within the deadline, right? Or, in simple words, showing that the response time of all tasks are shorter than the deadline. The result of this analysis is generally a formula, like some formulas have as the result somehow simplistic format, like the scalability analysis for a single core EDF. But others, in more complex scenarios, will show a more complex reasoning and might require some high skills on mathematics, not only in the final result, but also in all the steps that lead to that result, right? So the mathematical reasoning required for such analysis is very complex. And often some assumptions are made on the task model to facilitate this reasoning. Otherwise, it would be too complex to be reviewed and to be analyzed in deeply with the kind of rigor that the mathematical analysis requires you. And so that's how things are and that's how things move. On the other hand, with Linux, the approach is way more practical, right? But Linux itself, real-time Linux, is not a single thing. It's a set of things or a set of features that together try to provide a deterministic timing behavior for Linux, right? The approach used is more practical, as I said, and it usually starts with a metric that needs to be maximized. For example, the wake-up latency that is reduced with the parameter RT. And in the case of the parameter RT, some background was considered, right? The background was the usage of fully preemptive systems. And the difference between the practical and the theoretical analysis is that on Linux, the analysis is more made towards testing tools. For example, for the parameter RT, the cyclic test was developed and it is used to show that the system can schedule the highest priority thread within a given time, generally in the fewer microseconds, right? And then this approach repeats again and again and again for the other metrics. As I mentioned, real-time Linux is not composed of a single tool, but instead is a set of features, and among them the most important nowadays are the parameter RT that implements the fully preemptive mode, in which the system is approximated to the fully preemptive in the theory and gives us a low latency in the activation of the highest priority thread. And we also have the sched deadline, which implements an advanced global scheduler that tries to provide deterministic response time for tasks. And we also have the priority inheritance protocol on the mutex that try to avoid unbounded priority inversion, and among others, right? But these are the main features nowadays. And sometimes these features are easy to explain with words, but they require the years and years of development, mainly because the Linux kernel development is complex, right? And sometimes some assumptions are made to facilitate the development, right? For example, the preemptive model just approximate what is the preemptive model in the theory, and on the sched deadline, assumptions like that some overheads are tolerable, or that the all tasks can run on all the processors are made. But this is not fully compliant with the context of these techniques in theory, right? But anyways, otherwise it would be too complex to develop and too complex to integrate, and we might end up having nothing, right? So these things are just approximations, but they are good for many use cases, right? As I was explaining, there is this gap between the theory and the practice, right? The theory tries to provide answer for the problems that we have in the practice, but without considering all our restrictions. And we try to implement some algorithms from the theory, but without paying attention to all the assumptions that are made. But at the end, all this complexity, who cares about all this complexity, right? Nowadays, we have some workloads that require some level of determinism. For example, we have high frequency trading that requires some fast response to external events. And for these people, even nanoseconds counts, right? We have many embedded electronic devices that need to react promptly to some external events, mainly on telecommunication device. With the 5G now providing low latency communication, we need to have an operating system that provides this low latency as well, to not become the bottleneck of the latency. And we can also run this together with KVM, providing fast response time for external events on the guest virtual machine, and have like very nice results for this. And but generally, these use cases require just fewer real-time tasks, generally one task per CPU, right? And still, they are real-time cases, and they are pushing us for more complex use case, right? And these more complex use cases are requiring not only fast response for the highest priority thread, but deterministic response for a set of tasks, for a pipeline of tasks, right? Way more than one per CPU. And many of them requiring the synchronization among these tasks on many CPUs. And not only increasing the complexity of the timing guarantees that we need to provide, the usage of real-time Linux on safety critical system requires not only that system is able to do it, but also that we are able to explain why the system is able to accomplish it with some kind of tests and analysis that go far beyond the regular testing. They need some strong evidences that the worst case scenarios are found and that are be able to be handled in the case of default. And for some more extreme cases, the usage of formal methods is recommended to show that we really are able to address these worst cases accordingly, right? And then we return to this gap between the theory and practice. These new use cases are requiring a closer integration between what are the explanations that the theory can provide us and what are the results that we have in practice, and how can one thing match to the other. But luckily, we had made some progress in the recent years that bring closer this theory and the practice with some good results, and we will discuss this next. In this part of the talk, we will discuss a little bit the findings on this better integration with theory in practice in the study case of the preemption analysis, right? So in the fully preemptive kernel with the preemptor T, the threads becomes as preemptible as possible. And that's a side effect of moving out the non-schedulable context to the thread context and making the threads as preemptible as possible, as I said, by making them preemptive always, unless the preemption is explicitly disabled with preemptive disable and enable functions, or the functions that end up using it, right? So as a side effect of this change, when a new highest priority thread arrives, it is promptly handled with a very short delay. And this delay is demonstrated using the cyclic test tool that tries to create the arrival of a new highest priority thread and take these measurements. The results are so good that this delay is in the order of 100 microseconds, even on very pessimistic cases. And this allowed the Linux to be used on system with such a requirement. It allows the scheduler to take actions within 1 millisecond, so it improves the granularity of the scheduler decision, and it approximates the Linux to the theoretical preemptive systems in which many technologies are based on. For example, the SCAD deadline. The SCAD deadline assumes that system is preemptive. So, but why it's not good enough? It's not good enough because there is no clear description of the factors that cause latency. And so it's hard to provide an evidence that the worst case scenario was found. And so it's hard to convince more skeptical people like the theoretical community. So trying to learn from the theory, the thing starts with the creation of a precise definition of the system, the development of the algorithm, the finding of the worst case. And actually, for the preemptor case, the things should be simplified, right? Because the algorithm was already created, and we have like very good evidences that it actually works because cyclic test gives us nice results. So things should be easier, right? So why can't we try to explain this in the same terms that the theory uses, right? And we did it. So following that approach, we started creating a very precise definition of the synchronization of threads on the parameter T, considering these events that are important in the activation of the highest priority threads. And this resulted on a thread synchronization model for the parameter T, which was published on academic papers, right? And you have more information on the paper in the slide. Then we clearly define what was the property that we would like to analyze. And the property was the scheduling latency. So the scheduling latency experienced by an arbitrary thread is the longest time elapsed between the time A in which any job of this thread becomes ready and with the highest priority, and the time F which the scheduler returns, allowing this thread to start executing its own code. Then, with this in mind, we took that formal model and translate its properties and its specifications into a set of arguments that are commonly used in the real-time theory. From these arguments, we define what was the worst blocking that a lower priority thread can cause in this highest priority thread, delaying its activation. And we also defined how much interference interrupts can added in this time window. And voila, we end up finding a latency bound using these theoretical arguments. And it was good enough to be published in a paper, right? It's not the idea here to explain all the details, but you can read the paper, and there are also additional material in the page linked in the slides. So with that, we brought theory closer to the Linux kernel, right? But what else could we do? How can we turn the practice closer to what we see in theory? So to make that, we jumped back to the approach used on Linux, which is trying to create a tool that showed us these delays in practice, right? That connects the theory with practice. So based on the latency bound, we developed a tool that traced the system, because the model was based on trace, trying to show the value of those variables. And we did it. The tool is called RTSL. You can find information in the paper as well. And with that, we parsed the kernel events, trying to show what were the value for those variables. And with the value for those variables, we could state what would be the worst case scheduling latency. And we have some practical output out of the tool, right? And with that, we brought together the theory and the practice. And it was very welcome both in the theoretical side and in the development side, which was good. And one fear that people frequently have when we join the theory and the practice in the real time is that we could have like very pessimistic values, but that was not the case. So the theory was adequate enough to demonstrate that system has a bound, a safe bound for the scheduling delay, but it was also not just the side effect of editing pessimism. In that, if you look at the results shown in the paper that I'm showing here in the slides, even being pessimistic, the results are within milliseconds for many arrival curves of IRQs. And it only crosses the millisecond barrier if we use some ultra worst case. But still, even using this ultra worst case in the consideration of the IRQ arrival, they are still bounded, right? So the system converges, and that's good. So what are the final remarks of this section of the presentation? The absence of formalism didn't avoid Linux to have a sound preemption model. In that, the parameter T model was already deterministic. The thing that was missing was a precise definition of the problem and the definition of the behavior of the system under the terms used in the real-time system theory. And with that, we open the door for a new set of analysis that we can make on Linux. And even though some of these results shown that cyclic test was somehow optimistic, the values provided by the proposed tool show that Linux is still a viable option on the current scenarios, and it's really endorsing the fact that people would like to go further and use Linux on more complicated systems like the safety critical systems, right? So at this point, many people might be asking, is now Linux a theoretically proof real-time operating system? And the answer is obviously no, there is still a long way to go, right? The point is that the main metric for real-time system is the response time. And even though the scheduling latency is a fundamental step for it, it's not enough, right? The scheduling latency is just about when the task actually starts running and not when the task actually delivers the final results. And there are more points that affect the response time of the thread, and we still need to analyze them. So the next question is, so from where should we start? Should we start from the practice or from the theory? And the answer is that this is not a chicken or the egg problem, it's actually an evolution problem. And looking back at the preemptive RT case, we can see that the preemptive mode was something that existed in the real-time theory since like the 60s or 70s, where the theory was created and developed. And this was way before the starting of development of Linux. And the preemptive RT tried to bring Linux closer to this theoretical system, right? Until the point it was barely impossible to make progress anymore. So, and at that point, Linux was not fully matching the theory. And the next point was then to create a new theory that actually fits on Linux, which was closer to the preemptive, but not exactly that. And we saw that it was possible. So, trying to think in the way that the theory evolves and the way that Linux evolves, it seems that the way to go next is try to find the next problem that we need to resolve on Linux to make it a better real-time operating system, and then try to create a theoretically sound algorithm to address this problem, like based on some existing theory, and try to create a precise definition of how Linux implements this theory, finding the worst case, and trying to see if it matches or if it doesn't match with the theory in which Linux is based on. If it completes match, it's nice, it's perfect, it's worked on, we should jump to the next problem. But often it will not be the case because of the problems that we have in the practice. So when this is the case, we need to try to create a new theory, a new set of theorems, a new set of argumentation that shows that Linux is deterministic. And with the new theory, we have new methods, and with new methods, we have a new way to test and verify Linux behavior and improve Linux in the testing side. And also, we have new metrics to evaluate Linux and to follow the progress of these new algorithms and try to find things that might break this theory and cause regression. And this goes in the flow that Linux is going with the continuous testing and continuous integration of the operating system. And then we can try to replicate this approach on the next and the next and the next problem. So, but yeah, now we should jump to the question of what is next. So what are the next problems that we need to try to address to try to provide the answer for the response time of Linux, right? To the response time of threads that run on Linux. And we already have some ongoing work on this regarding synchronization, scheduling, and locking that we will discuss now. So the first problem in which we are somehow naturally applying such approach is the migrated disable one. In the preemptive RT, we have the migrated disable synchronization primitive, which is used mainly to replace the preemptive disable in the case in which the preemptive disable was used to hold a thread into a given processor to force a synchronization, right? So in many cases, when the thread doesn't actually need to have the preemptive disable, but instead just don't want it to be migrated, the migrated disable is used on the preemptive RT because by not using parameter disable, you can reduce the scheduling latency, which is the metric that the parameter RT tries to maximize. So that's why it's good. But on the other hand, it brings the side effect of breaking the working conservingness property of the multi-core schedulers. The working conserving property says that on a system with m processors, the m highest priority threads will be assigned to the processors. However, there are cases in which the migrated disable breaks this assumption. For example, imagine a system with two CPUs, and the CPU 0 and CPU 1 are busy running the two highest priority threads. Then the thread in the CPU 0 goes there and disables the migration. Then another thread arrives and it's scheduled in the CPU 0 because it's now the highest priority thread on that CPU. And then right after that, the CPU 1 goes idle. And in the current algorithm, the thread that is preempted on CPU 0 would be pulled to the CPU 1, right, to keep the working conservatives, but it cannot be pulled because of the migrated disable. And that's a problem. That creates idle time in the CPU 1, right? And well, but that would also happen in the case of using parameter disable. No, because if the parameter disable was used, it would the thread on CPU 0 would not be preempted at the beginning, so this problem would not happen. So we have somehow a dilemma here, because in one hand we break the scheduling latency, in the other hand we break the response time, and both are bad for real time, right? But we are trying to find a way out from it, and Peter came with an idea which is very promising. So his idea is, instead of trying to migrate the thread that was preempted, when the CPU 1 goes 0, it would try to pick the running thread if the thread that it was about to pull was the one with migrated disabled, right? And this should recover the working conservativeness of the process. And that's good. So Peter said that next steps he would follow would be to create a new algorithm to pull the threads on the RT and in the deadline scheduler, to add the trace points so we can observe and measure the case of migrated disable, so we can trace in the same way that we do with parent disable. And finally, he said that he was supposed to twist my arms to try to update the model to include these scenarios and the numbers, right? The idea is there, the new theory would be created to address this problem, right? And that's very nice, because this wasn't a forced occasion. It just popped up on the ELCE2020. And that's a good sign of the evolution of the Linux kernel development community towards having better real-time properties. That's actually very cool. Recalling here, so the working conserving is a required property for the current real-time scheduler. With migrated disable, we break this property. There is a way out trying to minimize this gap. But this kind of problem was, I never heard of anything in the theory, right, like this, right? So we need to try to find if there is something that approximates of it. This looks very much the arbitrary priority affinity, which is a problem that is now being handled at the real-time community. And there are some cases of a scheduler that tries to add this arbitrary affinity control, but it is something that we need to try to address in the theory as well, at least trying to find something that matches. And that's nice, because once we reach to this place, this will start influencing the decisions of the design of the schedulers, for example. And yeah, Linux is moving forward, and is moving forward in a nice way. So what else? What else can we try to use this approach? So the SCAD deadline currently does not support tasks with different affinity, right? Because it's a global scheduler. And sometimes we need to accept the tasks that are pinned to CPUs on the deadline scheduler. For example, some K-worker cases that are actually there. So at the end we have somehow a workaround to make them possible. And that is good because we make Linux going forward, but we are breaking some theoretical assumptions that we have on SCAD deadline. The same partition scheduler, which is an idea that I explained on the slide pointed, on the presentation pointed in this slide, might be a way to go that would reduce these kind of problems. But still, as I said before, arbitrary affinity is still an open problem and a difficult problem in the theory as well. And another thing that we need to try to address on the SCAD deadline is that it doesn't explicitly considers the overhead of the operating system. Like it doesn't explicitly considers the scheduling overhead or the scheduling latest that we talked before. And also the kind of tests that we do in the SCAD deadline, they are most based on the tasks run in user space and try to say if they achieved or not achieved the result before the deadline. But there might be some hidden behaviors in the scheduler that we could catch with formal methods, looking at the system trace. And I know that there are some groups working on it with results that will be shared soon. And that's something to keep an eye. Another problem is that in the preempt RT, we have the priority inversion protection using the priority inheritance protocol. The priority inheritance protocol is very nice for single core fixed priority scheduler, which is not the case of the SCAD deadline, which has each activation will have a different priority. So the highest priority thread is always a different thread, right? You don't have a single highest priority. And actually now we are trying to address this problem using the deadline inheritance. But there are some known issues with deadline inheritance that are explained in the talk which is referred in this slide. So one idea is use the proxy execution to overcome this problem. But still, it's a good mechanism, but we need to develop more the analysis of the proxy execution mechanism in the Linux kernel with all the restrictions that we impose, and that's also a very challenging problem. And so on. So we have problems to resolve. And it seems that the lessons learned are being put in practice actually in the kernel development by the kernel developers, because we are seeing the benefit of it and we are making progress. So, but looking backwards, Linux had an enormous progress in the last decade with preempt RT, with SCAD deadline, with testing in 2, and this is pushing us to have more and more use cases, and these use cases are requiring more, let's say, sophisticated analysis. So to conclude, the real-time Linux with the preempt RT is not only an integral part of Linux now with the merging taking place, but also in the culture of the scheduling development, right? And there are more challenges to come, mainly because now we can focus more in the response time as the main metric for real-time Linux. And this will make us to go forward, applying new techniques and trying to make them run in parallel with a theory and practice and the methods that can give us a better assurance that Linux behaves correctly, both in the logical and in the timing behavior. And there's a lot of fun work to do in the next decade. So that's it. It was nice to make this presentation, even though I would prefer to do it live and have a beer after this. But that's live how it is now, right? And I'm open for questions. Thank you.